fuori anche iniziale. Ok, volete fare l'introduzione?
No, non è collegato nessuno, giusto?
Per momento
In
no.
questo momento partecipanti? Ma è anche attiva la...
È tutto in diretta su YouTube adesso.
Anche in diretta su YouTube, perfetto.
Vai.
Allora penso che possiamo cominciare, magari Alessandro può fare una brevissima introduzione.
La presentazione di oggi viene fatta da Simone Bauco, un dottorando del Dipartimento di Ingegneria Civile e Ingegneria Informatica dell'Università di Tor Vergata qui a Roma, che ci presenta un lavoro svolto in associazione con lo Iasi del CNR che riguarda lo sviluppo e l'esplorazione di tecniche di model driven engineering per attaccare l'esecuzione di applicazioni complesse su architetture eterogenee. Prego, Simone.
In recent years, increasing complexity of computational problems has brought to the introduction of increasingly advanced hardware computing environments. Among these, heterogeneous computing environments have gained popularity, combining different hardware components into a single platform. As we can see, in the field of high-performance computing, the adoption of heterogeneous computing environments is an increasing trend. Today, 9 out of the top 10 supercomputers in the world are based on heterogeneous hardware. The main advantage introduced by this kind of computing environments regards the possibility to enable the execution on different hardware components and offload the execution based on the nature of the execution. This leads to improvement in performance and in energy efficiency, exploiting, for example, components such as the FPGAs. In addition, the introduction of more than one single hardware component allows to overcome some physical limits of the expansion of the single component, such as the phenomenon of dark silicon. On the other hand, shifting to heterogeneity also implies some programming challenges, because creating an application for heterogeneous environments requires producing several executable files for every single hardware component, and this requires expertise in different programming paradigms. Once these executables are available, it's also needed a mechanism for the scaling of the execution across all different hardware components. For these reasons, the adoption of heterogeneous computing environments in domains different from the ICT is today often limited. The major issue is that creating a domain-specific application targeting heterogeneous architectures implies dual knowledge both of the reference domain and the technological concerns regarding the heterogeneous computing environments. One common solution to cope with this kind of challenges is to adopt software architecture in order to abstract away, to introduce abstraction layers to reduce the gap between the reference domain knowledge, and the technological concerns. In this view, software architecture gives the possibility to create an overview of software system by means of design concepts that can be interconnected according to some architectural style. And this allows to emphasize structural and behavioral aspects of a software system, abstracting away marginal details such as the implementation details. To bring this idea into practice, we can use the model-driven engineering approach to define software solution through abstraction called models that are automatically processed to generate optimized low-level code. The generation of low-level code, however, requires the optimization logic, so knowledge of the reference target architecture. For this reason, we have introduced an intermediate representation in order to offer an abstraction layer to abstract away these details. So the main goal of this work is to adopt the model-driven engineering approach, as it can be seen in the figure, to streamline the development of domain-specific languages. We have a series of transformation, both from model to other models, such as the DSL to the intermediate representation, as well as a model-to-text transformation which compiled the intermediate representation in several copies of low-level executable files, one for each hardware component. This work is part of a larger long-term project which is called Domain, which is a comprehensive software architecture to develop domain-specific applications targeting heterogeneous architectures. This complex task can be seen from various logical perspectives, which are the stakeholders involved, and these are the application engineers, who are ICT experts having domain knowledge but ignoring the details of the underlying hardware platform. Then we have the high-performance computing engineers, who have expertise in heterogeneous computing environments. We have the optimization specialists that define planning strategies to orchestrate the execution across different hardware components. And finally, the software architecture expert that provides support in the actor model, which is the intermediate representation architectural style or model-driven engineering. So this is the reference architecture of domain. We have all the introduced figures that work on different interconnected logical components that are the language development front end, in which the domain-specific languages and the intermediate representation are defined together with the transformation assets. Then we have the runtime environment in which the execution takes place and the optimization model. At the highest level, we have the application engineers that work on the development of domain-specific languages and on the model-to-model assets, and the software architecture experts that provide support, as I previously said, on the intermediate representation definition and the transformation assets. The high-performance computing engineer work on the runtime environment, on the management of the runtime environment, while the optimization specialists define a subsystem called the optimization model for orchestrating the execution across all the different components. One of the key aspects in this architecture is the presence of the intermediate representation. As I introduced, the reference architectural style for this intermediate representation is the actor model. The actor model is a model for concurrent computation, which has the actor as the basic unit. Actors are autonomous and self-contained agents that process tasks in a concurrent way. Each actor has an associated isolated state and communicate to other actors through buffered asynchronous message passing. So each actor has an associated mailbox and a mailing address. In order to communicate with other actors, an actor needs to know its address. So it's defined a topology of actors which define the possible communication channels within them. One of the key features of this model is the absence of a global ordering. Each actor has a local ordering of events independent from the others, and these are related by the event ordering, the event activation ordering, that is the causal relationship between events occurring at different agents. For this reason, this model is well suited to represent a concurrent system such as the heterogeneous computing environment. So the presence of the intermediate representation, which is based on the actor model, allows to abstract away all the implementation details of the runtime environment, as well as the reuse of software assets. In this case, we can see that the introduction of a new DSL in this architecture only requires the definition of the domain-specific language itself and the model-to-model transformation to the intermediate representation based on the actor model. Shifting to the implementation, the intermediate representation has been implemented as a domain-specific language using JetBrains NPS as the reference language workbench, called the actor language. This language allows to define actors, messages, and the topology of actors. And here we can see an example of an artifact coded in this actor language that is structured in different parts. We have the definition of the types, for example, the payload of the tasks exchanged by the actors. Then we have the definition of external functions, that are opaque behavior that provide some functionality and can be invoked when processing a task. We have the definition of the behaviors, the actions, the sequence of actions an actor executes when processing a task. We have the creation of the actors through the create actor statement, providing a unique name for the actor, a behavior from the list of the created behaviors, and a fetching policy from the associated mailbox. Finally, we have the definition of the topology. For each actor, an actor box is created, representing the node in the graph, in the topology graph, and then links between actor boxes can be created to define all the possible communication channels. To plug this intermediate representation into the domains architecture, it is needed to create a series of model-to-text assets. Domain foresees a collection of these assets in order to transform the intermediate representation to several lower-level artifacts targeting different hardware components. We began doing this by designing a set of assets in a single model-to-text transformation targeting parallel speculative task-based runtime environment which is running on the CPU. In the future, we aim at extending this transformation to include other hardware components. One of the key aspects of the model-to-text assets is the application independency. In this case, when defining the model-to-text transformation, all the application-specific details should be ignored. To test this architecture into a real-world scenario, we defined domain-specific languages, and high-level domain-specific languages, which is in the field of the stream processing. This domain-specific language is called actor language, and it allows to define queries on data streams. So it's a subset of streaming SQL. It allows to the different statement to create named data streams as well as querying in a standard SQL way these data streams. To plug this language into the domains architecture, we have to define a model-to-model transformation targeting the actor language. The key strategy here is to extract a topology from the series of queries. For each query, we generate a set of actors, one for each SQL operator, and these are interconnected according to the ordering of the SQL operators. The data ingestion process is modeled and simulated by a special actor called data source. The streaming data source is a replay of the New York City TLC trip dataset, providing information about taxi rides in the area of New York City. We have defined the following set of queries representing a real-world usage. For example, it refers to crucial locations or aspects of potential interest. And for comparison, we have implemented the same set of queries using an off-the-shelf framework that is Apache Spark. The evaluation metrics are the execution time and memory consumption, and these are analyzed under varying the number of cores and the window size. As we can see in these queries, we have the SQL window operator that allows to aggregate tuples, receive tuples into 10 windows in order to apply aggregate operations, for example. So when a varying number of cores, we have fixed the size of this window, this time window, to 1800 seconds, while when varying the window sizes, we fix the number of cores at 4, that is the number of physical cores offered by the machine we used for the experiments. Starting with the results, we have the execution times varying with the number of cores. We can see in the case of Spark, which is represented by the orange line, a decreasing trend that becomes stable when reaching the number of physical cores. In the case of our system, called in this case actor stream, and represented by the blue color, we have a decreasing trend when using the physical cores and better performance than Spark, but in this case the introduction of hyperthreading worsens the performance. This can depend on secondary effect on core dynamics, such as the introduction of cache coherence protocols. In the case of memory consumption, both peak and average, we have a stable situation for both the system, having better performance in the case, lower memory consumption in the case of actor stream. When comparing the execution with the execution time of an optimized sequential execution, we can see a positive speed up in the case of actor stream when using the physical cores. As we have seen, the introduction of heterogeneity brings to a worsening of the performance, while in the case of Spark we have a negative speed up that reaches speed up equals to 1 in the case of the maximum number of physical cores, or in the case of hyperthreading. When varying the window size, we have a stable situation as regards execution times for both the system, with the only exception of very small windows in the case of Spark. Generally, we can say that in this case, our system reaches better performance than Spark. The situation is reversed when talking about the memory consumption varying with the window size. We have a stable situation in the case of Spark, while an increasing trend in the case of actor stream. We can see a direct proportionality between the window size and the memory consumption. This depends on the way in which the tuples are maintained when doing aggregations. In the case of Spark, minimal aggregation state is maintained, having a minimal state that is updated every time a new tuple is received within a window, while in the case of actor stream we have the aggregation of windows implies keeping all the tuples belonging to a window until the end when the aggregate operations are applied. So this explains this direct proportionality. In conclusion, we highlighted the difficulties in the adoption of heterogeneous platforms in domains different from the ICT. We introduced software architecture, architectural styles, and the model-driven engineering approach as tools to abstract away the technical details, facilitating the development of domain-specific languages. We introduced the domain platform as a system for developing application using this strategy. Then we highlighted the necessity and advantages introduced by the presence of an intermediate representation and the actor model as a well-suited architectural style for this intermediate representation. And then we presented a real-world case study to compare software solution developed using this strategy with a state-of-the-art framework such like Apache Spark. In the future, we aim at evaluating the entire platform, also extending the transformation to enable execution on different classes of hardware than CPUs, and then we want to introduce adaptive policies to plan strategies to orchestrate the execution on different hardware components. Thank you.
Okay. Thank you, Simone. Are there any questions? No question. Very good. So everything was clear. Good. So at the moment there are no external participants, so I think we can just close the connection and end the seminar. Okay, thank you.
Okay.
Thank you.
Thank you very much.